Alright, so in this example problem, we have a hoop of radius 0.25 meters and a mass of 2 kilograms. And initially it's rotating about its center. So a rotation is right here where I'm drawing the big red dot, and the rotation point is going to go into the page. But we're going to keep it parallel, so along the radius, and we're going to move our new rotation point over here along the edge. So once again, our axis is into the page. So they're parallel to each other, both going into the page, but they're a certain distance apart now. So we've taken the rotation point from being here at the center, and now the rotation point is along the edge of the hoop. So now, whenever it rotates, it's going to rotate about this point, so it's going to go sort of like around like this. Alright, so we need to figure out what the moment of inertia is, so I is our unknown. And since we are moving our axes, and it's parallel, we can use the parallel axis theorem, so that's what I've written down right here. Now, I went to the table in Blackboard that's linked underneath the constants tables, and I looked up what the moment of inertia equation is for a thin-walled cylinder or a hoop. Different textbooks have different phrasing for this. And it happens to look like the point mass 1 where it's mr squared. Where m is the mass of the hoop, r is the radius of the hoop. Now we need to do this right here. So the mass of the object is still the mass of the object, but we need to establish what d is. So originally our rotation point was here, and then we moved along the edge. So the distance d happens to be the radius of the hoop. So when we plug this in, we're going to take 2 times the radius squared for the original moment of inertia equation, and 2 being the mass times the radius squared again to handle the part where we move the rotational axis some distance d away that is parallel. And that gives us a moment of inertia that is 0.25 kilogram meter squared.